So welcome you all. So today we are going to discuss about the rectifier circuit. So we all know what a rectifier circuit does. A rectifier circuit is a circuit which will be converting an AC voltage or AC current to a DC voltage or DC current, and this process is known as rectification by converting an AC input to a DC output. So rectification refers to the process of converting an AC voltage or current source to a DC voltage or current, and the rectifiers are specially referred to power electronic converters where the electrical power flows from AC side to DC side. That is, in case of rectifiers, the electrical power will be flowing from AC side to DC side. So this is a basic block diagram of a rectifier circuit. Here the input is given is an AC input and we are getting a DC output from the rectifier circuit. Okay. Now coming to the classification of rectifiers, rectifiers are generally classified into two types, that is, one is single phase rectifiers and three phase rectifiers. Now both these single phase and three phase rectifiers are again classified into uncontrolled rectifier, half controlled rectifiers and fully controlled rectifiers. In that, uncontrolled and fully controlled rectifiers are again classified into half wave rectifiers and full wave rectifiers, and finally this full wave rectifiers is again classified into bridge rectifier and center tapped or split supply rectifiers. Okay, and you can see here both the single phase and three phase rectifiers are classified into uncontrolled rectifier, half controlled rectifiers and fully controlled rectifier. What do you mean by this controlling? Okay, that we are going to see now. Okay, so in an uncontrolled rectifier we cannot control the output, whereas in case of a controlled rectifier we can control the output. So in the case of semi-controlled rectifier we can partially control the output. So in case of an uncontrolled rectifier we cannot control the output, whereas in case of a controlled rectifier we can control the output voltage or current. And the uncontrolled rectifiers has only diodes, okay, whereas in case of controlled rectifier it will be having SCR or thyristors. Understand? Okay, in uncontrolled type of rectifier there will be only using diodes, where in the case of controlled rectifier we will be using SCR or thyristor. In the case of SCR or thyristor there will be three terminals. Okay, one gate terminal will be there. If that gate terminal is triggered, then only that thyristor or SCR will be on. But in the case of diode it will be having only two terminals, that is anode and cathode. So there is no triggering mechanism in the case of diode. So diode is, when we are using diode it will be an uncontrolled rectifier, and when we are using a SCR or thyristor, that rectifier will become a controlled rectifier. And if you are using both this SCR and diodes, it will be semi-controlled rectifiers. The controlled rectifiers needs a triggering circuit, whereas an uncontrolled rectifier does not need a triggering circuit. We all know that in case of SCR or thyristor there will be three terminal, anode, cathode and gate. So by triggering the gate terminal we can control the output of that rectifier in the case of controlled rectifier. So by varying the firing angle we can change the output in the case of a controlled rectifier, and there is no firing or triggering concept in the case of uncontrolled rectifier. So by varying firing angle in thyristor or SCR we can control the output of a controlled rectifier, but in case of uncontrolled rectifier we are using diodes only. So in diodes there is no triggering concept, and the cost of uncontrolled rectifier is less when compared to the cost of controlled rectifier, and output can be smoothly controlled in case of a controlled rectifier because there we can control the output. The time required to design controlled rectifier is more compared to the time required to build a uncontrolled rectifier. Okay, so these are the main difference between controlled rectifier and uncontrolled rectifier, and one more classification is there, that is semi-controlled rectifier. So in case of semi-controlled rectifier, we will be using both these diodes and SCRs or thyristor. So it will be semi-controlled. Okay. So this is a diagram of a single phase half wave uncontrolled rectifier. It is called as uncontrolled rectifier because in this rectification circuit we are using diodes for rectification. Okay, if you are using diode, it will be uncontrolled rectifier. So this is the input given to this half wave rectifier, and we are getting this is the output of an half wave rectifier. You can see here only in one half cycle there will be output. So calculating the expression for average voltage VDC will be equal to 1 by total time period, that total interval 0 to t V d theta. Okay, so we will be getting VDC as Vm by pi, and RMS voltage means root mean square voltage, means root of 1 by t 0 to t V square d theta, that we will be getting as V0, which will be equal to Vm by 2. And the rectification efficiency here, it will be around 40.6%, and the peak inverse voltage, that is the maximum voltage a diode can withstand when it is in reverse bias condition, that is Vm. Okay, and this is the full bridge configuration. Okay, not center tapped, full bridge configuration, full wave uncontrolled rectifier, and here you can see the output will be there in both the half cycles. Okay, and if you are calculating the average output voltage, you can see here the period will be from, this will be 0 to t and this is t by 2. So period will be from 1 divided by t by 2, 0 to t by 2 V d theta. Okay, so we will be getting VDC will be equal to 2 Vm by pi, and here output means RMS output voltage V0 will be equal to again 1 by t by 2, 0 to t by 2 V square d theta, root mean square value of output voltage. Okay, so we will be taking square first, then mean, then square root of. Okay, so we will be getting V out will be equal to Vm by root 2, and here also rectification efficiency is around 81.2%. In case of half wave it was around 40%, and here it is 81.2%. And coming to the peak inverse voltage, that is the maximum voltage a diode can withstand when it is in reverse bias condition. In case of center tap configuration it is 2 Vm, but in case of bridge configuration, that is what we have seen here, it will be Vm voltage only. Okay, so in the syllabus we have to study the 3-phase diode bridge rectifier basic principles only, and then single phase and 3-phase controlled rectifiers with R load, RL load and RLE loads. And for us only basic principles are there to study. Okay, now we are going to study about 3-phase diode rectifiers. This diode rectifiers means what? It will be uncontrolled only. It will be uncontrolled rectifiers. Okay, and previously we have seen the single phase rectifiers. These single phase rectifiers are suitable only for low to medium power application. So in the case of high power applications, that is more than 15 kilowatt, the 3-phase or polyphase diode rectifiers are used. Okay, so there are two types of 3-phase diode rectifier that convert a 3-phase AC supply into a DC voltage, that is star rectifiers and bridge rectifiers. And for the sake of simplicity, the diodes and transformers are considered as ideal. Okay, and the diode is assumed that it will be having 0 voltage drop and reverse 0 voltage drop and reverse current, and the transformer do not possess either resistance or leakage inductance. Okay, so these are the assumptions we are taking. So this is the circuit diagram of a 3-phase diode half bridge rectifier, you can see only one diode is used, so it will be half wave rectifier. And you can see here in the primary side we have used a delta connection, and in the secondary side we are using a star connection or Y connection. Okay, so this is the line A, this is line B, and this is line C. In line A diode D1 is connected, and in line B diode D2 is connected, and in line C diode D3 is connected. Okay, and load is connected here. Okay, between this line and neutral terminal. Okay, and this is a R load, that is resistor load only. Okay, so this same figure I had drawn here. You can see here the line voltage VA or line A connected to diode D1, and line B connected to diode D2, and line C connected to diode D3. Here also line A connected to diode D1, line B connected to diode D2, and line C connected to diode D3. Same figure I have redrawn here. And the phase voltage VA, which is equal to Vm sin omega t. Okay, and Vb will be Vm sin omega t minus 2 pi by 3. That is from line A, from phase A to phase B, there will be a 120 degree phase shift. That is what written here, Vm sin omega t minus 2 pi by 3, and Vc, which will be equal to Vm sin omega t minus 4 pi by 3. Means from Vb to Vc there is a phase difference of 120 degree. Okay, the one, and you can see here one diode is used in each phase. The cathode of the diodes are common. Okay, this is anode and this is cathode. The cathodes of the diodes are common, and load is connected between cathode and ground. Load is connected between cathode and ground, and source is connected to anode side of the diode. The source, the three sources VA, VB, VC, these sources are connected to anode side of the diode. And source is a Y or star connected source, and each phase voltages are having 120 degree phase difference. That is what written here. VA is equal to Vm sin omega t, VB is equal to Vm sin omega t minus 2 pi by 3, and Vc is equal to Vm sin omega t minus 4 pi by 3. So I am representing these three voltages here. VA represented here. Now VB I am representing here. VB means 120 degree phase shift from VA. You can see here this zero crossing point is 0, and here it is 2 pi by 3, means 120 degree. Now VC is drawn. VC will be 120 degree phase shift from VB. You can see here the zero crossing point is here, that is 8 pi by 3 or 4 pi by 6, which is again 120 degree phase shift from this VB. Okay, fine. So each phase voltage will be having 120 degree phase shift. Okay, that is what's shown in this figure. Now in this case, which diode will be conducting? Okay, which diode will be conducting here? So you can see here, suppose here I am having 10 volt, here I am having 5 volt, and here I am having 3 volt. In phase A 10 volt, phase B 5 volt, and phase C I am having 3 volt. So I am assuming that this diode D3 is conducting. Okay, diode D3 is conducting means we have already assumed that diode drop is 0. If diode D3 is conducting means here anode 3 volt means in cathode also we will be getting 3 volt, right? So here 3 volt means in this point also I will be getting 3 volt. So here also it will be 3 volt, here also it will be 3 volt. Okay, so here you see, here in anode it is 5 volt and cathode it is 3 volt. So whether this diode will be forward bias or reverse bias? this diode will be forward bias, because here in anode side it is 5 volt and in cathode side it is 3 volt. So if it is forward bias means this 5 volt will be coming here, right? Yes. So this 5 volt will be coming here. If that 5 volt is coming here, here it will be 5 volt, and here also it will be 5 volt, and here also it will be 5 volt. Correct. So now you can see here in anode side it is 3 volt and in cathode side it is 5 volt. So what will be happening? This diode will be reverse bias. D3 will be reverse bias. Okay, and you can see this 5 volt is coming here in D1 also. Okay, so here you see in anode side it is 10 volt and in cathode side it is 5 volt. So this diode also will be conducting. This diode conducting means this voltage, cathode voltage will be 10 volt, assuming that a diode drop is 0. So this 10 means here also it will be 10 volt. Here 10 volt means this both places it will be 10 volt. Okay, so here if it is 10 volt means you can see here in anode side it is 5 volt and cathode side it is 10 volt. So what will be happening? This diode D2 will become reverse bias. Diode D2 will be becoming reverse bias. So you can see here at a particular time only one diode will be conducting. 3 diodes are here, only one diode will be conducting at a particular time, and that diode phase voltage will be maximum. In which phase maximum voltage is there, that particular diode will be conducting. So if phase A is having maximum voltage, then that diode D1 will be conducting. If phase B is having maximum voltage, then that diode D2 will be conducting, and if phase C is having maximum voltage, that diode will be conducting. So this is the rule of thumb for this working of 3-phase rectifier. Understood? This is very important point. So in which phase maximum voltage is there, that particular diode will be conducting. This is an important thumb of rule in case of 3-phase. Understood? So I have told that which phase having maximum voltage, that diode will be conducting, right? So here the output voltage will be like this. I will show here. Output voltage will be like this. So from here to here. Okay, phase A is having maximum voltage, so it will be conducting, means diode D1 will be on. Diode D1 will be on, and from here to here diode D2 will be on, and from here to here diode D3 will be on. So the output will be the envelope of phase voltages. Output will be the envelope of phase voltages. And one more thing I have to add here, and each diode will be conducting for 120 degree. You can see here from pi by 6 to pi by 6 to 5 pi by 6, that is 120 degree, and from 5 pi by 6 to 3 pi by 2, and from 3 pi by 2 to 2 pi, that is 120 degree. So each diode will be conducting for 120 degrees, or each phase will be conducting for 120 degrees, and the output voltage waveform will be like this. So output voltage will be the envelope of phase voltage. Output voltage will be envelope of phase voltage. Envelope of phase voltage here. Okay, understand? Fine. Now we are going to calculate VDC, IDC, VRMS and IRMS. So this is our output waveform. Okay, and if I am taking this as reference line, you can see here this as reference line means VDC, which will be equal to, you can see here this will be 120 degree, and from here to here it is 120 degree, and from here to here it is 120 degree. So I am taking this area. Okay, if I am taking this area means VDC will be equal to total time period. Total time period is 2 pi. So 1 by 2 pi. You can see this is 120 degree. So half of that it will be 60 degree. 60 degree means the limit will be from 0 to 60. 0 to 60 means 0 to pi by 3. And this waveform from this reference point resembles a cosine wave that is starting from 90 degree. So Vm cos omega t d omega t. This 2 signifies, you can see here I am taking half of this area. So these 2 parts I have to add. So 2 times this into this 2 times, and you can see in total time period of 2 pi, like that 3 times it is conducting 120 degree, 120 degree, 120 degree, that is this 3. Okay, so after integrating we will be getting VDC, which will be equal to 3 root 3 by 2 pi Vm, 3 root 3 by 2 pi Vm, which is an important relation, 3 root 3 by 2 pi Vm or 0.827 Vm. Similarly, IDC will be equal to 0.827 Vm by R, because here we are using resistive load. So if we are dividing by load resistor, we will be getting IDC. And coming to the RMS value means root mean square value. This same average value expression, that is 2 into 3 divided by 2 pi, 0 to pi, and the square of this term Vm square cos omega square t d omega t, which will be equal to, while solving we will be getting 0.8407 Vm, and IRMS, which will be equal to 0.8407 Vm by R. Okay, since it is a resistive load. Okay, now calculating the diode current from here to here. VA means phase A. In phase A, diode D1 is conducting, and when diode D1 is conducting, D2 and D3 will be reverse bias. So in this, while phase A is conducting, there will be current in diode D1 only, because diode D1 is forward bias and D2 and D3 will be reverse bias. So at that time the current through diode D2 and D3 will be 0. Okay, and you can see here VB, voltage across line B, is maximum. So VB will be coming to the output, and at that time you can see VB is connected to diode D2. So this D1 and D3 will be reverse bias. D1 and D3 reverse bias means D2 only will be conducting. So the path will be like this. Okay, path will be like this. So V2 will be coming across D2, the output across D2 will be coming across this load resistor R. So at that time D2 current will be passing through D2, and the D1 current and D3 current will be 0. And similarly in the third case, that is when phase VC is more, so diode D3 will be conducting, and diode D1 and D2 will be reverse bias. Okay, D1 and D2 will be reverse bias. So current will be coming through only D3. Okay, current will be coming only through D3, and D1 and D2 will be having 0 current. So taking the average load current, we will be getting graph like this. Okay, in when VA is more, diode D1 will be conducting. When VB is more, diode D2 will be conducting, and when VC is more, diode D3 will be conducting. So this will be the load current waveform. Okay, and now calculating the diode current and RMS current. If I am taking this as reference point, okay, this is reference point, you can see here, and I am taking this area. Okay, I am taking this area. So ID1 will be equal to 0 to pi by 3, means total, this is 120 degree, this is 120 degree, so this will be 60 degree. Okay, 0 to pi by 3, Im, this wave resembles to cosine wave, Im cos omega t d omega t, and this 2 means total time period is 2 pi, so 1 by 2 pi, and this 2 indicates I have taken this half of the area, so it should be into 2. Okay, one part and second part, so it should be into 2. So while solving this equation, we will be getting ID1 which will be equal to 0.2757 Im, and coming to the RMS current will be root of this term into square of this term. Okay, so we will be getting ID1 RMS which will be equal to 0.4854 Im. Now coming to the performance parameter, we will be getting rectification efficiency here. It will be around 96.77% when compared to single phase configuration. It has again improved. Ripple factor is around 18.24, only 18.24 ripple content is there in this circuit, and we will be getting VAC which will be equal to ripple factor into VDC, which will be around 0.15104 Vm. Okay, so this is all about 3-phase half wave rectifier. So I have told this 3-phase half wave rectifier for explaining the 3-phase full bridge rectifier. Okay, so with this I am concluding this lecture. Thank you.